Hi, and welcome to this video on radiative forcing, a key concept that helps us characterize how environmental factors affect our climate. So what is radiative forcing? Radiative forcing refers to changes in the energy balance of Earth's climate. Put simply, it measures the impact on the energy entering and leaving the planet. This balance is affected by many factors. The most infamous and severe is carbon dioxide. There are two types of forcing, positive and negative. Positive radiative forcing increases the rate of net energy added to the Earth, leading to warming. A classic example of this is carbon dioxide, which acts like a blanket and traps heat in the atmosphere. Ironically, positive forcing isn't so positive for the Earth. On the other hand, negative radiative forcing reduces the net rate of energy added, which can slow down warming and even cool the planet. An example is aerosol pollution in the atmosphere, which reflects sunlight back into space. By measuring the radiative forcing value, the impact of different factors can be compared, indicating how much they change the net flux of the system, which strongly correlates with warming or cooling the climate. To explain in greater detail these radiative forcing agents, a simple model of the Earth's climate will be very useful. But first we need to explain what flux really is. So what is flux? Flux is a measure of the rate at which energy passes through a surface, with units of watts per unit area. And net flux is the difference between incoming and outgoing flux. Radiative forcing is also measured in flux, as it represents a change in net flux due to an environmental factor. An example of flux which is very useful for our simple model is the flux of sunlight across the surface of the Earth. This incoming flux is predominantly formed of shortwave EM radiation. Some is reflected due to Earth's albedo, and the rest is absorbed and re-emitted as long-wave radiation from the surface, with the emitted flux given by the Stefan-Boltzmann equation. However, this long-wave radiation is heavily absorbed by greenhouse gases, trapping heat, which is then re-emitted as black-body radiation, some heading back towards the Earth. This is the greenhouse effect. Now, with our simple climate model, we can dive back into radiative forcing and cover some key examples. But first, I would like to address that there are some different definitions for types of radiative forcing, and each one is useful for modelling different components of the climate. Unfortunately, it's not quite as simple as a single definition, but the most useful definition for radiative forcing is effective radiative forcing. Here we're measuring the change in net flux at the top of the atmosphere, and we allow the entire atmosphere to adjust its temperature, only the ocean is fixed. This gives a good idea of how the forcing agents will actually affect the atmosphere and global temperatures on a shorter time scale, and it's very useful for comparing the impact of different factors. Alternatively, we have equilibrium response. Temperatures are adjusted everywhere, and the net flux of the system is zero. This shows a longer-term view of how a system would adjust to a radiative forcing, going through a number of changes to restore the overall net flux to zero as the system reaches a new balance. Now, if you compare these different temperature curves for equilibrium response and effective forcing, we can see they are similar. This is why ERF is so useful. It gives a solid prediction of where the climate is headed even before the system is fully settled. Now that we have refined our definition of radiative forcing, let's reapproach our model of greenhouse gas emissions as a positive forcing agent. We can take our climate model and increase the amount of greenhouse gas in the atmosphere. This increases the amount of long-wave radiation captured in the atmosphere, and a larger amount of heat is retained and re-emitted towards Earth, hence positive forcing. Other examples of positive forcing include solar activity. This changes the incident flux on the Earth and operates on an 11-year cycle. Building large cities and road networks, which are predominantly dark materials, reduces albedo, reducing the reflected shortwave radiation worldwide. But let's look on the bright side. Let's have a look at some examples for negative forcing. Aerosol pollution such as sulfur dioxide creates a reflective layer in the atmosphere. This reflects shortwave radiation from the sun back into space. Some scientists have suggested intentional aerosol pollution could be a solution for global warming. Unfortunately, sulfur dioxide is the main component of acid rain, and this idea has mainly been forgotten. Volcanic eruptions are also a natural source of aerosol pollution, containing a lot of sulfur dioxide. Although overall forcing is still positive, these aerosols do offset a large portion of positive forcing. Perhaps surprisingly, deforestation is also an example of negative forcing. This is because trees are quite dark, and cutting them down increases the albedo of the Earth, meaning that more radiation is reflected into space. To summarize this video, radiative forcing is key for quantifying how human activities and natural processes influence Earth's climate. Even though factors like aerosol pollution or volcanic eruptions can slow down warming, the overall positive anthropogenic forcing continues to drive temperatures upwards, contributing to the climate change we see today. Thank you all for watching this short video.